Okay, so in the morning you've seen the first notions of data assimilation. I know it's not easy for every one of you. I've discussed a bit during the break, and so I'll try to make it as easy as possible in this second session, which is a bit more advanced. Especially we are going to talk about Kalman filters and the use of ensembles of simulations. I think when we are talking about HPC, making ensembles of simulation, a lot of simulations to represent our phenomena is something that is well, quite suitable, and we'll see what we can do with ensemble of simulations. All right, so I'll first go with the Kalman filter, okay, classical Kalman filter. We'll see that in high-dimensional space can be applied as such, so that's why we move to other filters, especially the Ensemble Kalman filter, which I think is not too difficult to understand, so we'll go through this one in details. And okay, I'll explain a bit other kind of filters that have different properties, like deterministic filters, reduced rank filters, we'll see. And after that, I'll move to what we can do with ensembles of simulations. It's not only used within Kalman filter, it can be used in different applications, for instance, quantification and other form of data assimilation than the one you've seen so far. All right, so first I put back the same notation, or essentially the same notation as this morning, so we made sure you won't be lost. So we still have this state vector, which is going to be x. So, okay, can be xb for the background. It's going also to be sometimes xf, as you saw, I think this morning. F for the forecast, it means. You will have this xa, a for analysis. So every time you have x, this is the state of your vector. So that's all the variables that your model computes. So if you have a meteorological model, you have temperature, pressure, everything in one single vector. Usually in your model, you discretize everything, so you just have a finite number of variables that your model computes, and all of them are put in a big vector in the order you want, and that's what is in the state vector. And if your model is deterministic and you fix the initial condition with a given state vector, then the trajectory after that is always completely determined. Okay, so you have all variables in the state vector. Okay, then. Important notion is errors. So you have background error or forecast error when your x is actually a forecast. It could be xf in that case. And it's going to be the distance, or the discrepancy between what you've computed, the x, and the true value for that x, xt, the true values of all the components of your state vector. Okay, and so you've seen that Sophie discussed a lot about these errors because it's really the key. Because what we want to do in data assimilation is to actually decrease the uncertainty, so somehow, so it would be to decrease the variance of this error. That's the goal with all available information. And this, the error is a vector. Since we don't know the truth, we model this as a random vector. This here we don't know the error for sure exactly. Otherwise, we would just remove it from what we forecasted. So we model it as a random vector, and this random vector as a mean, and more important as a variance. Okay, so that's the error variance B, or sometimes going to be called PF for forecast, which is simply the variance of this error here, epsilon B. So you compute it, it means just classical formula, you remove the mean and you compute this. So of course this is a matrix because the random vector epsilon is a vector, so its variance is a matrix. And so we focus a lot on this. Then we compute an analysis, which is an improved state, hopefully. Improved in the sense that it's the discrepancy between this state computed analysis and the truth as an error, which hopefully is lower than the error of the forecast, or by lower I mean that it's going to have a lower error variance, A, okay, or PA, depending on the algorithm. Okay, and then we have observations. So observation, it's usually at much lower dimension than the state. it can happen, it can be the reverse in some applications, but usually that's what you have. So you have a few observations in some locations that observe some components of the state, or combination of components of the state, okay, and we try to make a better estimation of the state based on that. And so we have the observational operator that you've seen that maps from the state space into observational space. So you apply H, which is nonlinear here, it could be linear sometimes, to the state, and then you have, if the state, for instance, is a forecast from the model, you apply the observational operator, and somehow it's a forecast of your model at the observed locations. Okay, and then we introduce also, you've seen observational error, which is the distance between what was measured and what would be the application of the observation operator to the true state. Okay? So if you have the true state, exact state, you apply the observation operator, and then you get and you make the difference with the observation, and you get what is called the observational error, because observations are not perfect either, and so we have to balance between the two. You've seen that in this morning. Okay, and then this observational error has a variance as well, which is called R. All this can depend on time, then I'll put a subscript H in that case. All right, so you've seen blue, just to recall. So we assume that the background error, so that somehow our forecast or our background or first guess, XB, is associated with an error epsilon B whose mean is 0, so so the background is unbiased. Observations, if they are unbiased, then their error is also of 0 mean, and we assume uncorrelated errors between what we've produced, XB, and the observations. Okay. All right, so this one is a matrix, and every component inside is the covariance between observational error and state error for some components. Then, under these assumptions, the blue is the best linear unbiased estimator. It's a linear estimator, that's a L of blue, because you have a linear combination of XB, or first guess, and observations. It's unbiased because we'll make sure that the error we make on the analysis, so that epsilon A, XA minus XT, is of a 0 mean. Okay, so the analysis is still unbiased. We retain the properties we had on the first guess and on the observations. And it's the best estimator in the sense that it has minimum variance, or the trace of the error variance of the analysis, so that the capital A I've shown previously, the trace of this one is minimum. Okay? So the sum of the variances of all individual components in the analysis error have or minimum. Okay, and so you've been explaining that. You have this gain matrix, two forms here. First one, probably easier to read, and you see you have somehow the ratio between B and B plus R, because you have this some train between observations and first guess, depending on how much confidence you have in one or the other. Sophia has shown example in this morning. So that's the base. I mean, the blue, it's in most data assimilation methods somewhere, and the point is really to compute this one usually in the best way possible. Okay. And of course, you see that XB, that's what we compute usually, while observations we obtain. So the challenges could be in the observational operator, but usually it's not that difficult to find a good one. And then in B and R, okay, we don't really know what to do. R is associated with observations, so you might find some clues about how reliable or your instrument for the measurements and things like that. Okay, you can find something, but B is very difficult. It's a very big matrix, as Sophie mentioned, and she shows different strategies to compute it because that's really a key point in the data estimation scheme. All right. So there is one simple algorithm before going to the Kalman filter, which would be an improvement over this one, which is called optimal interpolation. It's like the 4-divar if you have a linear observation operator. But it goes this way. So you're going to compute blue every time you have observations. That's the point. So that's mainly the algorithm. So here reads the algorithm. You start from an initial condition at step H equals 0. You have your initial state, XF0. Okay, so that you start from that, and to forecast the next step, you'll first check whether so you are at time h. You want to go to the step h+1. What you're going to do is to first compute an analysis at time h, and then move forward your state to the next step at h+1. So what you do, you have if observations are available, then you complete blue, as we've seen previously. Gives you an analysis at time h, which is that combination of your forecast x fh and on your observations with a matrix. Okay, and after that you make a forecast. You start from that new state, the analysis, which is supposed to be an improved state, and you let the model integrate until the next step h+1. Okay, so that's a sequential algorithm. If you have no observation at some point, you just let the model run. Okay, you start from the forecast you had. You can't make corrections on it, and then you move to just to the next step by calling the model, applying the model to the state, and let it update the state. So that's the algorithm. Okay, maybe, yeah. So that's a classical one. It has a drawback, which is, okay, you can in this one you compute the analysis. You compute you can also compute its error variance, and this error variance looks like this one. So it's PA, it's the error variance of the analysis. It depends on the error variance of your forecast XF, okay, which is PF. Okay, and this is the formula you get. One of the way to write it. It's I minus KH times PF, or you can write also this way. So and the eigenvalues of this PA are lower than the eigenvalues of your PF because you've decreased the variance of your error. Okay, that's fine. On your analysis, that's normal. But then. So, because on the data simulation process, you are constantly adding new observations, so decreasing the error against time. Okay. But in the previous algorithm, we never took that into account. Okay, we can compute PA, we have the formula, but then we don't do anything with it, and so we move to the next step and then use again PFH. Depends on H. You can make it time dependent, but it's not going to depend on what you've previously done in terms of data simulation. You have to guess it every time to prescribe it in the algorithm. But the truth is, normally your estimator is getting better and better because you are adding observations to correct the state against time. All right. So optimal interpolation is going to just provide the forecast, but it's not going to provide any error variance for that forecast. And that's what the Kalman filter wants to solve, actually. It's going to make the different step. It's going to analyze this stage, so you have the analysis, you have the variance of its error, okay, PA. Okay, you can do that in optimal interpolation. And the forecast stage, when you will start from the analysis and then run the model from that, you'll get the XFH+1, just like in optimal interpolation, but you'll also be able to compute its error variance, PF. Okay. So, yeah, okay. So this PA is better than the PF somehow, okay? Then you go through the model. The model might introduce errors, okay? So I said that somehow the error variance is going to decrease. That's not exactly true. It's going to decrease because the observations during the assimilation process. But at the same time, while you make this time integration, the model is going to add some more errors because the model is not perfect. So you have these two things going on at the same time. Increase of errors because of the model that is imperfect, but also decrease of the errors because of the observations you assimilate. It's not even completely true because the model itself might also decrease errors. Depends how it is. Okay, If you have just a linear model with all its eigenvalues less than 1, it's going to converge to 0, and maybe that's the exact state to which you want to converge. So it's possible also the model kills some directions of the error or rotates errors in the state space. So many things can happen, but essentially what happens is that the model increases the errors, and at the assimilation stage, you decrease them. Okay, so we start from this PA. Okay, that's what I was saying. So the model from one time state to the other, the imperfect model will increase the error. And we need to introduce how much error it's going to introduce, and this is this epsilon m for model, so it's a model error. And this is the error that is added from one step to the next. It's not exactly this. Okay, we define it that if you have x, so xt is a true state at time h plus 1, it's going to be the model equal to the model, so from time h to h plus 1, time integrator. You apply this model to the true state, but you don't get the real state at time h plus 1 because your model is imperfect. So we say we have this model error. And I put a note because I think this can be a bit confusing to call that model error. Because, okay, if you imagine you have an exact model MT, which is able to give you the exact, the exact state for the next step. If you have this model MT, which is exact, so you provide it with the exact state and gives you the exact state at the next step. What you would like, I guess, to define in terms of model error will be something like the difference between what your model has computed and what the true model would have computed, right? Usually, when you define an error, you take the quantity you have and you remove, you take it minus the exact value, and that defines your error. I think that's more logical like this. But in the way it's defined here, actually, it's the opposite. Just okay, so it doesn't really matter because the sign, okay, doesn't really matter, but just that's the way it's defined usually. So I mentioned it to you. You can make the difference between these two equations, and you will find that epsilon is defined this way. It's just a note, so don't be confused about it, but okay, it's called model error. That's the way it's defined. And similarly, okay, so we have here definition of model error. I put it again on this slide, same as previously. And again, we'll make some assumptions. You're getting used to these kind of assumptions. We'll assume that the model error has 0 mean. And we'll introduce its error variance, QH, okay, so it's typical stuff. We're doing that all the time. And also we assume that the model errors are uncorrelated with the analysis error. That's to ease the computations to come. So now that we know what kind of error is added by the model every step, we can maybe try to compute what's going to be the forecast error variance after one step of the model, because we know what we are going to add in terms of error. So here we go. The forecast error at time h plus 1, it's the state at time h plus 1 minus the true state at time h plus 1, okay, usual definition. And we replace xf plus h plus 1 by its value, which is m, the model applied to the analysis from the previous step. And so we also replace this hth plus 1 by this definition, okay? Here, see, because it comes from the definition of the model error, exactly what was written on your right. And so the forecast error at time h plus 1 looks like this. It's the model to which the analysis error to which you apply the model minus model error. And if you compute, so the expectation, since the expectation of these two, error analysis error and model error are 0, you still have 0 mean on the error of the forecast. Nice. And you can compute the variance. It's fairly trivial to do that. And what you obtain in the end, you have two terms. Okay, if you put this expression of error into the variance here, you expand, and you have some cross terms which are zero because we assume uncorrelated error between model error and correlation between model error and analysis error, and you have these two terms that remain, which are obviously the model times the analysis error times M transpose plus model error. So the error variance of the forecast is going to be the error error variance of the analysis transported by the model this way, plus the model error, I mean the variance of the model error, which adds to the, yeah.
Sorry, can you clarify a little bit the lack of correlation between the error of the analysis and the error of the model?
Uh-huh.
The error of the analysis is contaminated by the error.
Well, yeah, that's a good point. If you, I mean, it's contaminated, but here what you have is the error on the analysis at time h, and you're going to add a new model error for the next step, which you can assume to be uncorrelated, because the error in the analysis does not depend on the model error from time of model error of time h, but only on previous ones. So if they're uncorrelated in time, for instance, it can be a bold assumption, but then it's true. Okay. Well, there would be a lot to discuss around these things, but I mean, even generally, all the assumptions we make, like any error. I mean, take any of them, observational error, and so on. That has zero mean, you know. To start with, I mean, we are pretty optimistic. We call them epsilon. That's also another thing. So there are a lot of assumptions. Then you can do things like, for instance, if you have not zero mean and you know you have an estimation of that mean, you can remove it in the equation, and then it works again. So you have tricks, and but it's it's a big point how all these assumptions. In practice we break a number of them. That's true. Okay. So here's the forecast error variance. We have an expression, an analytical expression for it, so it's perfect. We just use it, and we have the Kalman filter, so that's done. Kalman filter is the same as we've seen previously somehow. So you start from initial condition and its error variance because you are going to propagate it. So you still need to prescribe it, but just in the first step, at the initial step, and then after that you make an analysis step when you have observations, which is here. You compute the analysis and its error variance. Then you propagate this analysis and also propagate the error variance, so that you get the forecast error variance PF at time h+1. Okay, and if you have no observations, okay, you can just apply the model and also propagate its error variance. Okay, but you start from PF because you have no analysis at time h. So this is a Kalman filter. It's a very successful one, being used a lot, at least in low-dimensional systems. That is when the size of the state X is not too big. It's used a lot in automation, for instance. The names come from Rudolf Emil Kalman, which is an American born in Hungary. I think he passed away this month or the previous month. Okay, so, and he published this in a paper, I think, in 1963. So that's okay, getting a bit old, but now it's used a lot, and there are a lot of variants. So in time, what's happening? You've seen this picture, the first picture you've seen today with Sophie. That you have the state here, one component of the state, say. You have the time here, and the model makes time integration until you have an observation, say here. You compute an analysis which is going to be a linear combination of the two, your state and observations. You start from that, and again, when you have an observation, like you make a correction, and so on and so forth. So just sequential data assimilation. This is true for optimal interpolation, for Kalman filter. That's the only difference between the two, is that you propagate error variances as well in the Kalman filter. Okay. Yeah, okay, I put some notes. Okay, maybe there are a few things that I'll leave to you, you read later, but the thing is, if you, if you assume you're in a Gaussian, so far we've never assumed that we were a Gaussian, okay? Just assume zero means on the errors, we have some assumption on the correlations, but we don't need to be Gaussian anywhere. But if you want to make the links with Bayesian estimation, where you are going to estimate the full probability density function, then to get the same formula, you need to make the assumption of a Gaussian distribution in this Bayesian framework. And if you do so with the proper variances, I mean the natural ones, you will see that we actually compute with the Kalman filter exactly the mean and the variance, so the first two moments of error. And so that's why people are referring to Kalman filters as Gaussian filters, or second order filters, because we look at the first two moments of the distribution. And in the linear case, when the model is linear, then we have exactly the exact distribution through their first two moments. There are also with 4D vars that you've seen this morning, when you use all observation on the time window to find out the best initial condition, and then to have an estimate along time. You can show that the Kalman filters and the 4D var and the given assumptions, in the linear case essentially, they coincide at the end of the assimilation window. Okay? Not in between, but at the end, yeah, they coincide. So there are links. You've seen the formula. You feel you have that blue or that cost function. These are all very linked. And you have seen also the Bayesian framework somehow with the maximum a posteriori this morning. So all these things, I mean, they play around the same ideas. Okay, the good point with Kalman filter is it computes the state error variance. Okay, you make a 4D var, in the end you have a state estimator, but it's not so easy to get the error variance. But there are some disadvantages also. Here, every time you make that analysis, somehow you perturb the model. And after that, you might have some transient periods because the model is not balanced anymore, or you break more or less some physical constraints. Okay, so it can be a bit shaky sometimes. That's an inconvenience. Okay, also Kalman filter is formulated in the linear case. Okay, while 4D var is more naturally formulated in the nonlinear case. Okay, but okay, still, we badly want to use it, so even we make an adaptation for the nonlinear case, where we're going to lose optimality or the properties I've shown previously. You just use the Kalman filter and hope it's going to do well. So it's derived is a linear case. And when you have a nonlinear model, which is usually what we have, then you do the same for the analysis step because the model is not there. Okay, just apply the analysis as usual. And for the forecast, you will just call the model to forecast the state, EnKF. You use a full model. Okay, but then you have a problem with the propagation of the error variance. Okay, so that PF, because here what we've done previously was okay because we had this linear form for the model. So what we do in practice is that we replace. Okay, we use here in the propagation the tangent linear model so the Jacobian matrix, if you want, of the model. Okay, you derive it at the point where you have the analysis. Okay. That's what you use. So you linearize somehow, and you use this linearized model to propagate the error variance at that stage. And so that's an approximation. Of course, the error variance is going to be modified and due to the nonlinearity. We don't take that into account here. Okay. Also, the observation operator can be nonlinear. So we do the same kind of trick. So whenever we can, we use just the nonlinear observation operator. That's in this, computing of the innovation, y minus hx. So we use a nonlinear model here simply. And whenever we need, so in the matrix computation, we use the linearized observation operator similarly. And so that's for the computation of k and of PA. So in the end, the extended, what the so-called extended Kalman filter reads just like the Kalman filter, exactly the same step, except that when you can apply the full observation operator or model, then you do, and when you cannot, when you have this matrix H or M, then you use the linearized version. Otherwise, runs the same. So that's the extended Kalman filter. Actually, you can just take this algorithm, and when your model is linear, you're going to get back the Kalman filter simply. Okay. You can also use, just a side note, because I don't want to go too much into these things, but you can also use the Kalman filter in order to make parameter estimation. In which case, you define what's called an augmented state, which will include the state, plus the parameters you want to estimate. And you define a new model, that's your new model somehow, which doesn't change U, and just updates the state with a given U. And then you need to introduce that PF, definition of PF, at least PF0, in the initial step of your Kalman filter, you know that. But since you have an augmented state, then your error variance for that state is extended as well with the values I've put here, correlations between, covariances between state error and parameter error, and the variance on the error of the parameter U. And so you need to provide that at the initial step, and then you can apply the Kalman filter, which is going to give you this. So it's going and estimate, okay, you have no model error here as well, so you put 0. And then you can apply the Kalman filter. It's going to update U, because you have error correlations between U and the state at some point. Even if you start from 0, it could happen, because your state depends on the parameter, most logically. And also you have an estimation of how reliable your parameter estimation is, because here you have the variance of its error. But okay. Okay, I wanted to discuss a bit with the computational cost, because it's a HPC things here. So, but here, okay, there is one big issue. The Kalman filter actually can't be applied in high dimension. That's clear. Even with a lot of power, it's just impossible, because at least nonlinear case, this propagation of the error variance is very expensive. It's huge. So imagine, that PA or its size is, say, 1 million by 1 million. If your state is of size 1 million, but yeah, your state can be higher. 1 million, it's not that big state. Huh? It's a good one, but can be 1 billion sometimes. And so you can have a very huge state. But even if 1 million, okay, so to start with, the matrix is so big, okay, 1 million times 1 million. So you can't store it, okay, but might not be the main problem. But here you have this linearized model that you need somehow to apply to every column of PA, if you see. Just this part, this operation here. So it's somehow it's 1 million call to the linearized model. Okay, and the linearized model, well, it depends on your application, but it might cost as much as the original model. Okay, and if this is the case, then you have 1 million call to your model every step, and usually that's enough to say it's just impossible. And you do that again here. Okay, so it's just intractable in practice, and for large-scale applications that we are interested in, like geosciences and biology or whatever, in many cases. It's still useful in small dimension, and Kalman is very successful. But here, for high dimension, no. Okay, so we need to do something about that propagation. Okay, and you already have hints in the morning by Sophie about this. So we want to maybe get into a reduced space for that matrix so that it's not so big. Or we can also sample it. So I have some points that are going to sample this error variance. So from these samples, you are going to compute an empirical variance. And these samples can be determined either deterministically or randomly. So I'm going to start with the random part, where we are going to replace this error variance by an estimation of this error variance based on samples. So I put some references on data assimilation if you want to go. Sophie provided others, but it could be. Okay, I recommend you. Yeah, this one is easier to understand, I think, in the beginning for anyone, I'd say. I think it's a nice one. This one by Con, I think it's good to make links with estimation theories were written. In French, you can have a look at this PDF online by Marc Bocquet. And there are many other introductions. And now, so we're going to move towards the so-called ensemble Kalman filter, which tries to solve that problem of propagation of the error variance from one step to the next, using an ensemble of simulations that we're going to sample the error, and then from this ensemble of simulations, we can have an approximation of the error variance at every time with low cost. So we generate an ensemble of states somehow. So that's points in the state space. So different states. I'll put this exponent brackets m to indicate that this is the mth state in our ensemble of states. Okay? Every time. So we'll have some forecast for every. We have an ensemble of forecasts. We have capital M such forecast every time. We also have, in practice, capital M analysis. And we'll make use of these forecasts and analysis to estimate the error variance. And just simply, we'll say, okay, from them, we compute an empirical error variance. And this is our estimate for PF with XF, M, and with XMA, it's going to be for PA, of course. So it just replaces completely the error variances. So when we have, we have this ensemble of states from which we derive a mean, okay, empirical mean, XFH. Which is going to be our forecast, actually, in the end. Okay, that's, if we want to make just one forecast, this is going to be this one. And it's going to be the average of all the ensemble members, the ensemble states. I'm going to explain later how we compute these. And the main point, I mean, the motivation for doing this is actually to replace PF by the empirical variance, that you can compute from the XMF. Okay, can't point anymore. So I think it's just classical formula. Maybe you're not used to write it with vectors, but if you think in terms of 1D, this empirical variance, it looks like 1 over number of sample minus 1 plus the sum of your samples, XM minus X bar, the mean of your samples squared. Okay, that in statistics, that's what you would do if you have samples, okay, from a distribution. If you want, you can compute the empirical mean by just averaging all these samples, and you can compute the empirical variance, okay, by this formula. Okay, so it's just the same here. It's just written in higher dimension for vectors, and it reads like this. Okay. And for those who made statistics, we have m minus 1. You could put 1 over m, okay? 1 over m minus 1 is for this estimator to be unbiased. But that's just a detail, okay? You don't be bothered by this. And so we use it to compute the forecast error variance, PF, and also the the analysis error variance, PA, from the analysis we have here. So the question is how to compute this, XF and XFM and XAM. But if you have them, then you're fine. You have an approximation to your error variances with a few members. So the point is not to have 1 million members here, okay? Otherwise, it's going to be, as computationally intensive as getting propagation for the P as well, okay? Going to be the same size, but we have just a few of them, which hopefully will give us a good approximation to the error variances. Okay, so oops. Okay, so I put back this formula. Okay, you can write it in another way, in the square root form as well, which is very useful form, where essentially your PF it's one matrix times so the square root of P actually times its transposed, and in that square root you just put the values in column. You put the values of your states minus their, so the departure to the mean of the states, okay? And then you have M columns for capital M columns, where capital M is the size of the ensemble. In each column, you have the departure of each column M, so you have the departure between XMF and the empirical mean. So you put that in columns, and this gives you the square root of PF as computed by for classical formula. You have also factor 1 over square root of m minus 1, but essentially that's what you get. So that's a convenient way to write it as well. Okay, maybe it's becoming... can do the same easily to compute, this term you've seen, P times H, PF times H transpose, H, PF, H transpose. You see that in the computations. Okay, you can directly use nonlinear observation operator to make approximation. So it's kind of nice to make all computation when you have this kind of form. That's what I'm just mentioning. You have this kind of approximations that are useful. So in the ensemble Kalman filter, you don't have just one state, you have an ensemble of state. So here is the Kalman against time, and here is the ensemble Kalman filter against time. You have different trajectories. Okay, so it's just one component of the state. Okay, it's not just because otherwise, the model is each. Okay, whatever. It's not so important. Okay, so you have different members, and when you have observations, you are going to compute an analysis for each member. Okay, of your ensemble. And so this one may go here, this one go here, this one goes here, and this one goes here. They get closer to the observations, for instance. And these new points are analyses. So these are the XMA. And you start from them and make a time integration with the model for each one of them, which give you as many trajectories here that you can see. And so it gives you some forecasts, the XMF. And once you have observations, you compute an analysis again and gives you a new XMA, from which you start for the next cycle. Okay? Simple as that. Just you do the same as previously, but for many members, just not just one. And all these members of all these states are supposed to properly sample your uncertainty, essentially. That's the point. And the ensemble Kalman filter, so it reads like this, the algorithm. It's similar. You start from, this time you start from an ensemble of states, not just one. But you don't need anymore the error variance for these states because it's somehow embedded in the ensemble. So that's all you need are the ensemble of initial states. And then you move on. If you have observations, you compute the analysis, you compute just blue for everyone. Except that the point was how to compute this K matrix. So because you have this PF, this PF is computed, as I've shown previously, as the empirical variance of your ensemble. Which means that the analysis for all the members, they depend from each other through that matrix K, or actually through P. P depends on all the members. So when you make an analysis for one member, okay, it's made independently from the others in terms of what you use here for the state and what you use for observations. Okay, well, it's the same observation, but you can do the computations independently, but except that you really need to share the ZPF, which is based on all the members. That's the link you have between all the. That's why you can't have one simulation running and alone. You know, you need, when you have to make an analysis, you need all the members to be available and to compute the analysis for every one of them. Oops. Okay. And once you've computed this analysis for all the members, you propagate the ensemble here. Okay? For every M, you apply the Jeu model and so on, what I've shown previously. When there are no observations, you do as usual, you just forecast from the state. Okay, just mentioned that usually you're supposed to make perturbations on the observations. Although they already have some errors, are not perfect, you had also uncertainty on these ones. Based on the error variance you assume for them. Well, okay, I put the explanation why in the next slide. The same algorithm otherwise, but we do that so that that the analysis error variance has a proper, the proper value. Otherwise, if we don't make perturbations on the observation, we miss that term actually. Okay, that's more or less a detail, but I wrote it down. So then what's the computational cost of the ensemble Kalman filter? Well, okay, the first thing is you always have the analysis that costs something because you have to invert, you know, this matrix, HP, H transpose plus R, that costs, okay. But what's going to be driven really is the number of members you have in the ensemble, how many trajectories you are going to have in your ensemble. So usually you have between 30, 100 members, that's typical, let's say. Well, that starting to cost quite a lot. But you see that one good point is that in between two analysis stages, you make the time integration for every model, and you can parallelize this. It's completely trivial because you just have independent runs of one model, and then you can distribute it easily. So that's also what's happening to people to use that. But also, yeah, if we are talking really of HPC with large architectures, we have much more cores than just 30 or 100 still. So okay, so we are not going to use all the core if we just do something like this. So it means that also every member in the ensemble needs to be integrated by a parallel model again. So it doesn't mean it's okay. It doesn't really solve the. You are not using like that also all the computational power anyway. Okay, but it's still convenient. You have a part of the parallelization which is completely efficient because you just have to distribute the computation, and you lose nothing by doing this. I mean, the speed up is just perfect. So yeah, if we look a bit more about the computational cost, so you can have a cost sometimes in the observation operator because sometimes it's pretty complex. And it can happen if your observations are radiances from a satellite, and your model is an atmospheric model, you might have a radiative transfer model in between. I mean, so the observation operator can be sometimes more complex than the model itself. It can happen. So it can happen, this one costs. Yeah, the size of the ensemble I've shown, usually it's the driving variable for the cost, and number of observations, of course, because of this inversion, because this is of the size of the number of observations, obviously, because yeah, you see R, which is the error variance for the observation. Okay, as I mentioned, so the forecast analysis error variances are never computed explicitly. Sorry, we always make use of their square root form, so it saves a lot of space. It's much smaller because we have just the square root at just 30 to 100 columns, size of the ensemble, so it's not 1 million columns. And okay, I mentioned already that we have a coupling between the analyses. And the question now that you might be asking yourself is how we generate these ensembles of states and of forecast. So we want to sample the errors with that. Okay. So we need to make an ensemble that's going to take to take into account all the errors. So what and the errors we need to identify is first the errors on the inputs, on input parameters that are not on the state but some forcing. I mean, like if you're doing, I don't know, if you're just working on an atmospheric model, you have force, or on a metallurgical model, for instance, you have forcing from the ocean. So if the ocean is not part of your model, it's a forcing, it's some input data, which is not computed by your atmospheric model, but is needed as input and is surely erroneous as well. I mean, there are errors on it, and that's part of the parameters that are uncertain. If you're doing air quality, for instance, you have a lot of uncertainties in the emissions. It's not computed by the model, which only transports pollutants in the air. But this, okay, and you need to take into account this error in order to have a proper estimation of your state error variance. The model itself, we often forget it, but because I mean, like you can make perturbations on inputs, like Monte Carlo simulation, essentially. That's what you would do in Monte Carlo simulation. You would perturb inputs and make different simulations, and that's exactly the same idea here. I think that's yeah. So, but what is often forgotten, is that the model itself is imperfect, and sometimes the model itself leads to maybe higher errors on the inputs, so or similar. So. And it's not that easy to take that into account, but what we try to do then is to use different models, not just one. Of course, the numerical solver, that's a special case for you. Yeah. In the model, you have the equations that are imperfect somehow because that's the physical part. The model is imperfect. The physical model is imperfect, but then you also need to discretize the equations. And you have errors coming from the numerical solver, obviously. In time, space, and this also contributes to uncertainty. Okay, if you're in geosciences, for instance, I think for different variables it doesn't matter so much because you have so many uncertainties elsewhere, like 50% uncertainties on many inputs and error in the model. So it's a lot, but for certain variables, it's clearly the numerical solver is a big issue, especially if you have, say, if you have a stiff system with very different time scales. For instance, very tough to integrate, and on some components you will make a lot of errors. Okay, that's an example of errors on the input side to make. Yeah, so here are some pictures. Not equations anymore, just a few pictures now, where you see. Yeah, because I have to say, this ensemble now it's getting more and more important in all the major weather forecast centers in the world are computing ensembles every day. Okay, they're not just making one simulation; they're still making one at high resolution, but they're also making like 30 or 50 simulations to constitute an ensemble at lower resolution. But still, it costs them a lot, and they all do that. Okay, that's. For uncertainty quantification, especially. So that's and this is an example of this is at Fukushima. Okay, that's Japan, and here you have Fukushima, and here you have wind directions and speed, that's the length of the vector, for different models, different simulations from different ensembles in the world. So. Yeah, because here I took, a few members of Météo France ensemble, a few members of the European ensemble, a few members from the US ensemble, and so forth. Not all of them, because it would be too many arrows. And that's what you can get. So there you have you see a bit some uncertainty in the lengths, but okay, it's not that bad. This is another example. Where there are more differences. Here, maybe even more, you see, starting to have quite some differences. And you have this one as well, okay? And also this. So at some point you pick what you want, okay? But it's not exactly true because you have somehow a density. You see, you have more arrows this way, so you kind of somehow a density behind this. And this is really important. For instance, yeah, there is a known during the Fukushima disaster. I know this thing because I work with ERSN, which is in charge of radio protection and nuclear safety in France, and they made operational simulations during Fukushima accident for French people living in Japan or for industries there and so forth. So to know where the plume, the radionuclide plume was going to move. And all models in the world make simulation operationally, and there is a big episode where the plume gets into the land, okay, in this direction, and there is a lot of deposition there on the ground, okay, of radionuclides in these conditions. I think maybe because of snow or because of rain, I'm not sure. But you have a lot. And after the facts, when you measure radioactivity, you see this big region where you have all the deposition that still remains, because this is things that remain for a long time. What was deposited is not what was in the air and just moved away. It's what was deposited. So, and after the fact, they measured it and saw it. But no model was able to reproduce it, at least operationally, because they used simulations that were going in another direction. But the thing is, when you look at closely, in the ensemble of metallurgical simulations, there were models that were telling, okay, it's going to go into the land. Okay, so that's why if you use an ensemble, then you can have an idea of the risks. Or if you just use one simulation, deterministic simulation, you can miss completely what's going to happen. So, and sometimes your ensemble is going to be good. I mean, telling you this, okay, you have a pretty good confidence that you are not going into the land, but here, okay, you're not sure. Okay, so that's an example of output of models, and these models are going to be, these outputs of metallurgical models are going to be input for other models like dispersion of radionuclides and others. So we need to take that into account, and you see that people, they make an ensemble, and this ensemble somehow discrete. I mean, it's a sampling of your uncertainty, as you see here. That's exactly the idea. And here it's an example of, if you make different ensemble simulations. Here you have 6 simulations, and here you have the deposition of radionuclides, somehow, okay, maximum during some period and so forth. But you see, you can have different shapes, really different shapes. You have a lot of uncertainties. And so your members, your XFM, they can look like this. And they will tell you in which regions you have agreement between all these ensemble members, and so low uncertainty, and regions where, okay, it varies a lot because someone, okay, here it says there's nothing, while another says there's something. Here you have a lot of uncertainty. And it's going to show into your PF thanks to the ensemble. Okay. So it means also, it's the same algorithm again, ensemble Kalman filter. And just change one thing. You can have some perturbation on the inputs to generate your ensemble, and you can also use different models. You just generate them different trajectories and apply the ensemble Kalman filter as usual. Okay, so it's very practical. I mean, it's easy somehow because you need to. If you're already doing some Monte Carlo simulations, for instance, then you can just apply this. It's very straightforward. Okay, so 2 classical references on ensemble Kalman filter. So you see it's not that old, but it's very successful. It's implemented so much because it's so easy and it gives good results as well. Okay. So now I have I wanted to show you a practical example on a shallow water model. So it's a 1D shallow water model. Okay, so you have some of you know this thing very well. It's a simple one. So W is the height of your water. Okay, and V is the velocity. Okay, And so we compute the height of some water area in 1D against time, and that's what this model does. And we have on the left, you'll see we have a constant inflow. So you'll see that we have some water coming in, and on the right we have a homogeneous Neumann condition. It means that water is going to get out, just simply out of the domain. It's like open boundary. So it's discretized with 100 grid points, so which means for these 100 grid points you have the water height and the velocity at each of these points, which means that the size of the state is 200. Okay, the two variables at the 100 grid points. But in practice, just for simplicity, here I'm just going to show the water height. We will only observe the water height as well, and also assimilate only this. Make no correction on the velocity. Just leave it there. And we'll start from a step function, just a step function, and see how it goes. And we'll observe. So that's at some point the simulation you have the water height. It's 1 until 1.03, and here you have the 100 grid points, and we'll make observation at three locations around 80. Just 3 locations. Here we observe the water height, and we'll use that for data assimilation. So we'll introduce errors, you'll see, and see whether data assimilation can compensate for the errors we've introduced. So it's okay. I wanted to make it a bit interactive. So I'm running the showerwater for once. So it's a truth-like program. It's going to generate the truth, which is the truth. Just the real. I'm going to show how it goes. So we start from you've seen the step function. And then we let it run. Well, so what's happening is that we have zero velocity in the beginning. So the step function, splits into two waves somehow. Which going on the right and the other going on the left. That's what you see here. You have this split in the middle. Okay, you see these two, and you have an inflow here that and that's the reason why you have higher water height on the left. Okay, so that's the truth. Okay, that's what we want to reproduce using using some erroneous simulations. I'm going to show which one, and using observations just here at IT. Okay, so we make a forecast. Oops. And this one, the error we introduce is that we don't have this initial step. Okay, so we just start from a flat water, and this is our erroneous simulation. And here it goes, it's in blue. You see nothing happens here because there is no initial step. You still have this inflow that changes the water height on the left, but that's all, okay? And so you have errors here, you have error here, because you didn't have the initial step. So can data assimilation change that? So then we apply some optimal interpolation that we've seen previously. Okay, you see, it's a bit longer, still fast, and this one is going to assimilate observation at 80, and so the observation operator is fairly simple. You have 3 observations, okay? So you have 3 rows into the observation operator, okay? And it's going to be, the size here is going to be, say, 100. Will be 200 if you put also the velocity in the state, which we should do, but okay, and simplify. And you observe, say, at index 79, 80, 81. These are the locations where you observe. So your observation operator is going to be full of zeros, and you have 1 here, then zeros on the first column. So this is for the observations that observes at location 79 in your state. Okay, so over there. And for the other one, you have a 1 here at position 80 and zeros. And for the last observation, okay, just 1 at position 81. So this observation operator extracts from the 100 water heights on your that you computed the values at 79, 80, 81. Not sure about the index exactly, but that's the idea. Okay, so that's what you have in H. Because you observe exactly at grid points also. Huh? If we were observing in between, we would make linear interpolations and so. Okay. And so let's see yeah, another thing. So that's H. We also need to prescribe B. I just put identity to start, and for R, I put identity as well. It's not the same sign, of course. B it's 100 times 100, and R it's identity size 3 by 3. Okay. Let's see how it goes. I made the simulations already, so I'm going to plot all these in in red. You have optimal interpolation. In blue, you see up when you at 80. When you arrive at 80, when there is a difference between observation in green and what you've simulated, then you have a difference. You have this y minus hx, you see, in the correction of the analysis. So you have xa, which is your forecast, plus k y minus, okay, I should put maybe the time. So as long as this one is 0, which is the case in the beginning because everything is flat at 80, at locations 80, because the wave has not arrived yet, this one is 0, so your analysis remains just the forecast. You do nothing. But as soon as this one is not 0, then you are starting making corrections. That's what you see at some point. Yeah, start again. So you have a wave, and when it arrives at 80, then you have a difference, and the optimal interpolation gives you a different result from the simulation without assimilation. Okay, so let's. I'd like to have a look at the difference. Yeah, this is at one step. You see, when it's starting, you're starting making corrections at 80 because you have a difference between what you simulated and so because the waves arrived, you have this. So and I plot here actually the analysis and the forecast at one step. We'll zoom because here we don't see, but I plot the two because I think it's interesting to see. Here it is. Yeah. So so in red you have the forecast, and in black you have the analysis. XA. And in green, you have observations. In blue, this is a simulation without assimilation. So at some point, you have a forecast, which is this one. You have observations that arrive again, one here, and one here, and you make a correction. So what you observe first is at the observed location here, for instance, the analysis in black is just in between. And actually halfway between the forecast in red and the observation in green, right? Why is that? That's because in B and R, we put the same error variance, 1. So for every, at the location 80, for instance, or 79, the error variance is supposed to be 1. And on the observations is 1 as well. If you remember what Sophie showed, I mean, you have somehow in K, you have the ratio between B and R plus B. Okay? If you make the computation, you will see that actually, if you make you have equal confidence between the two, so you end up in between, just exactly in between, halfway. Okay. So that's why. That's the case here, that's the case here, and that's the case here. And then after, if you look at locations that are not observed, just this one here, and this one here, you see that the forecast and the analysis coincide. Okay? which is a bit unfortunate. We just correct at location where we observe, and we don't observe so much. Why that? That's because we have no error correlations or zero covariances in B. Between two locations, the covariance is 0 between the errors, okay, at these two locations. So it means that you observe at one location, okay, but on another location, there is no correlation between the errors. So what you've learned at the observed location, you can't apply at the non-observed location. But had we something different in B, some error correlations, then we could make correlations elsewhere, okay? I put this one because I don't know exactly what to put. And that's difficult. I mean, what would you put? It's going to depend on at what time you are. It's going to depend on your model and so forth. It's complex. That's why we are so interested in Kalman filter and so forth, because we don't want to prescribe this kind of matrix. Even in such simple case, how are you going to, what kind of error variance are you going to introduce? I mean, error covariance. It's very difficult. So, and so if we can make, if I, for the test, we can, if you like, we can also change. So I put, you see in the code, so it's not really for, B equals 1 times identity, and or I put or equals 1 times identity, okay? But now, if I want to be closer to the observation here, if I want my analysis to be closer to the observation, what am I going to do? I'm going to decrease R, the error variance on the observations, to put more confidence into the observations. So the error variance is 1, but okay, for instance, I put 0.2 instead. And if I run my optimal interpolation again, and I take this one, I think. No, that's not what I wanted to show, but okay. It's going to be about the same shape, you know. Or maybe you can already see it's closer, but I did not plot the right one. Oh, yeah, this one. Okay, and then I zoom, and we'll see. You see? It's much, much closer. Okay. You can compute it yourself. I mean, in the weekend, I'm sure that's what you are going to do. Huh? You will have fun with this and compute how close you can be, depending on R and B. So, of course, you have more confidence in observation, so you're closer. Okay, but still, if you look at the complete simulation, it's not so nice because, all right, you're starting getting something here. You're getting closer, it's nice. But at some point, you see, oh, it splits again. And you have somehow two waves, and this one is going to get out, actually, of the domain. And at some point, you will be left with this one, which is even, so somehow your analysis or forecast from optimal interpolation is worse than what you had initially, because what you had initially actually was okay in this region now, at that moment, and you are left with this extra water you don't want. So data simulation is not magical. It can worsen things somehow. Also. That's also the message, and I know so it's not easy to find out, to understand why. I mean, to find out why. Understand? I think it's not difficult. What's happening here when you had you correct the water height, you do that without modifying the velocity. But in the reality, you have these waves that move, so it has some velocity that keeps everything consistent. Okay? So but in the data simulation part, you just modify the water height. You don't modify the velocity. And it's a bit like putting this step function in the beginning where you have two waves that it splits in two waves, and that's somehow what happens here because the velocity is not right. Okay, so the whole question in data simulation: what to observe, what kind of variables, and when, and at what locations, and so forth. Because otherwise you can even worse the things. Usually you don't. But just to mention to you that's not magical. Okay, now we'll do the Kalman filter. The ensemble Kalman filter. We can't afford the full Kalman filter. And this one already you see it's going to be the Kalman is going to be ensemble Kalman filter with just 15 members. It's going to be a bit slow. And yeah, you see. And let's see. So we have errors on the initial step, right? On the truth, we had no step function. I mean, our erroneous simulation, we have no step function. We have only a step function in the truth. So here are the ensemble members. We sample the initial error. So we make different randomly. We produce different step function at the initial stage. Okay, that's our ensemble. We don't know which one is right, but we know that's the error we're making. So we generate this ensemble. And so a bit later, let's see how it goes. Yeah, so every single, this one is with, yeah, we haven't reached 80 so far, but so here you have every simulation, you know, they are run independently in the filter, unless you have analysis at some point, but otherwise they just run. And they all start from step functions, so they just make these two waves, okay, all the simulation, and that's what you see here. All the members, they have this kind of behavior. Can show you in time. Take the F. Take. Yeah, so in time you start from this. It's a bit slow to display, but you can see that, okay, you have these two waves that, for the 15 members. Okay, just and this is the sample of our uncertainty, and this is with this one that we compute our empirical variance. Okay, empirical error variance. So let's have a look at the mean, how it goes. Oh, nothing happened when we crossed 80, by the way. It's a bit disappointing, but we'll see why later. And so, okay, the average is not exactly 0, so we have some residual here on the Kalman side in red, and the truth is in green, and we were not able to reproduce the truth yet, but we are going to succeed later on. Just to show you, essentially, here it's like as if you had no assimilation. Okay, so your forecast with the Kalman ensemble Kalman filter is the ensemble of the members, and this is what I show in red. That's just the mean of all the members. It's not exactly 0 because of sampling errors, but you see the point. It's not satisfactory. And also, so here actually data assimilation is activated but doesn't work. Why is that? Let's have a look. The thing is, in the Kalman filter we have this OR. I kept for observational error. I kept this OR matrix. Okay, but that's an issue. Do you see why? So I assume that my variance, so my standard deviation, the standard deviation of the error is 1 for observations. Okay? So let's have a look at the values here. Oops. We observe the water height is between 1 and say 1.03. So if you have your error is of magnitude 1 in standard deviation, it's absolutely huge. Okay? So you don't trust observations, they give no information if they are so poor. Okay? Because then you are between 0 and +2, and with probability 68% if you're Gaussian or something, so it's very, very bad. So you have no, it's pointless. And okay, but why did it work previously? That's because I put R and B of the same magnitude. I prescribed them. But they are meaningless, actually, for that problem. But it still works. Why? Because in K, if you remember, you have somehow you have like B H transpose, HB H transpose plus R minus 1, and you can multiply, so that's K. You can multiply B and R by some factor alpha. I multiply by alpha B, alpha, multiply R by alpha, any factor, and you see, it just cancels out. You simplify, because you have this over this, so alpha goes away, and you have the same K. It's just a matter of how much confidence you have on the observation versus confidence on the simulations. Okay? The scale doesn't matter, just compute the analysis. That's what it means. Okay? It's not completely true that doesn't matter, because at some then when I'm going to compute the a posteriori, so the analysis error variance A, then it's going to, if I multiply everything by alpha, I will have a problem here, because I have alpha B here. So it's going to be wrong. I mean, so I'm not encouraging you to put anything, but just for computing this analysis, you can, yeah, you can have a factor between, multiply everything by a factor, it's fine. But here, in the ensemble Kalman filter, the Kalman filter computes, evaluates the error variance itself. And if you, so how is it? Yeah, if you look at this one, you see that the spread of the ensemble will give you an idea of the error variance. It's between, essentially 1 and 1.01 or something. So essentially the standard deviation is 0.01, more or less. Okay? So the variance is 10 to the power minus 4. Just the square of this. So somehow my B here at some location is 10 to the power minus 4, and actually lower elsewhere. And R is 1 in what I put. So, of course, I trust absolutely. I don't trust observations at all. So I'll trust this one. So I'll put 1 minus 10 to the power minus 5 for R, and run the Kalman again. And this time I expect that observations are taken into account. And then when this arrives around 80, something happens. Okay, so I'm going back to my command. So we'll see just the mean for the moment, okay? We'll see whether the forecast of the Kalman, the mean does something. Okay, ta-ta. Here we are. Works well, you see? Then you get back the full wave. And I think you've noticed as well that not only we get the wave at the location we observe, but look at here. On the left also we get the wave. Although we do not observe there. Okay? But we were able to get it. Why? Because we have this, because we have correlations between the errors at the two locations, at the two waves. If you remember the, maybe this one, and if you remember the shape of the ensemble, should clear figure. You see, you have the two waves somehow, and the members are in the same order, so there is high correlation. So between here and here, the correlation is very high. Between you compute the difference to the mean, and then compute the empirical variance this way, and you will see these variances are high. And that's why you have correlation, and when you observe at one location, you can also correct at the other one. So that's why it's so important to have proper estimation of that matrix B or PF, okay? And the ensemble Kalman filter, if you sample properly your uncertainties, it's going to do that, just that. Give you the proper estimation, and then it's going to work very well. We can have maybe a look also at the ensemble against time this way. Now that we have, so you'll see another thing. So it's a bit slow, but you see the ensemble propagating, and now we're going to observe around 80. You see, all the members gradually are getting good. And so what you remember when you make in Kalman filter, actually you have two information. You have the state, the mean we've seen, okay, good. But also you have an uncertainty estimation on your mean, because you have the error covariance matrix with the ensemble somehow. And what you see here, after data assimilation, the spread has gone very small. So it means you trust very much then your new state. And this is true because it's a good one. So you have also very small error variance associated with your new state. Okay, and so that's also very important information. And actually, what happens nowadays is that we want to have uncertainty quantification. I've shown you with Fukushima or the many applications. You want to have uncertainty quantification, and one way to do that is just applying a Kalman filter. So people are doing sometimes just Kalman filter, not to improve forecast, just to have an estimation of uncertainty. Also a posteriori uncertainty because you take into account observation. Okay, so it decreases with time. So that's a posteriori uncertainty. That's important to understand. It's not a priori. You use observations. But also from that, you can, at some point, if you have no observation yet, you can stop and then just make the simulation without observation in the future. That's what it's done also in many applications. You have no observation, that you make forecast with your ensemble, and the error is going to grow again. And this gives you an estimation of your uncertainty, but starting from an analysis of something of good quality. And so you improve your forecast and have an uncertainty quantification with it. I wanted to show you also the matrix PF or PA. Here it is. So it's at time, let's say, maybe whatever the time. You see, it's at some time step 150, and this is how it looks. This is the empirical error covariance matrix. So it's you've seen the formula computed from the ensemble members, and so it's symmetric. Of course, it's a variance, and you see that actually you have two locations because of the two waves. So on the diagonals, it's a variance of the error at the individual locations. So it's very outside the waves. It's just zero because all the members coincide, so there is no error variance. That's what you see here on the diagonal. Until here, when you arrive on the one of the waves, you have some variance which is higher at the top of the wave because the values are higher. Okay, so you have more amplitude, so you have more uncertainty on the top of the wave, and that's why it's increasing and then decreasing again along the diagonal. So I'm moving along the state, and the same on the second wave. And then if you look at just one location, so okay, take here for instance the top of the wave on the left wave, you look at the covariances on one line, so it's the covariances with all the other points. So it's zero with the points where nothing happens. There is high correlation with close neighbors, a bit less correlations with neighbors a bit further in the wave, and then you have high correlations with the other wave, okay, that you see here. That's what we expect. We understood in the first place, and that's why when you observe one of the two, the other one is going to be correct. Okay. So I think I'm done with the example. We can make a break. I think that's a proper time, unless you maybe have questions or. I don't know.
So questions?
I'll be there anyway. Yeah?
So the example that you just showed, you could really reduce the spread with 3 observations out of 100.
Sorry? Yeah.
So in the example, you had 100 points.
Yeah.
And with the filter, you could really reduce the spread with having 3 observations points. At 3 points, you had observations.
So that's the points. So which points were the observations? That's the question?
Your point in the example you showed, those
yeah.
3 points round about 80.
Yeah, here. 3 points.
Would you be able to reduce the spread? What's the minimum number of observations that you would need?
I think just one would do. But it really depends on what confidence you have in observations. If you have if you have low confidence, then the spread is not going to be reduced a lot. If you have high confidence, so very low R, then okay, observation is the truth, and then every one member is going to be very close to observation soon, very soon. So that's a big parameter, I'd say. Yeah. And the number of observations, one would be enough here. I just put 3 because of, yeah, to illustrate analysis, and it's better, but yeah.
Maybe it's also related to observability condition that you can explain a little bit.
Yeah, because then when you make some corrections, you're going to, well, you're going to have some propagation in the model, and so sometimes you can observe things that come, especially when you are in some inverse modeling or you're trying to estimate parameters. You want to have some you need to have some influence of what you are looking for with respect to the location where you observe. Okay? And so you can, in certain system, try to evaluate what part of the state you are going to somehow observe directly or indirectly with the observations you have. And basically it should translate in the end by some error variances or not that you find. So there are special properties about that. You could look at this like observability and also controllability, which is linked. Yeah, so there is big questions where to put observation, what kind of observations to put in general. So that's like network design problems that that are very difficult problems, because then you need to find where to put the observation so that the assimilation is good. So it's an extra level on top of assimilation. There are people working on it, that's yeah. Especially as if you know here, you have the a posteriori error A, okay, and so you can try to optimize this one. I mean, to make sure that the trace, for instance, this one is minimum by playing on H. So where to put the observation, what kind of observation operators, or where to put the observations. So that would be basically what to do. And because you know the a posteriori error variance here, it does not depend on the observations. So the confidence you have on the analysis state does not depend on the observations. It just depends on R actually, and H and B. Okay, so just the confidence you have on the observations, where they stand, so that would be H, and what confidence you had in the initial state B. And so you can play, virtually, you can put observations virtually without having the actual values for these observations. So that's, but doesn't mean it's easy anyway. But just notice, so you would like to optimize at B with respect to some parameters in H. But if you want to work with them, there are interesting problems around this. Yeah.
Other questions? Okay. So see you at 4 and 10. Let's say 5, so that we will start at 10.
Okay. Well, I guess we can start again. Yeah. The sooner we will end, right? Okay, I see. So I wanted to show a few of the filters. You see, so you've seen the Kalman filter, full filter, impossible to apply in high dimension, and then we move to the ensemble Kalman filter, where we sample the error with our members randomly. So that's a way to randomly sample the errors, and there are other ways which okay, that I'm going to present. So there is one, I think, which can be especially adequate for HPC. So I wanted to show a bit the idea, which is the LETKF, so local ensemble transform Kalman filter. praised by many. So I'm going to show a bit what's happening inside. There are two ideas between this one. So it's still using ensembles, and there is one idea which is not the one I want to emphasize, but I have to explain it because that's the way the filter works. So the thing is, if you look at the analysis here, you have XA, which is XF plus K times the innovation. The question, if you look at K closely, then you see that you have PF here, and K is equal to PF times something. And when you use an ensemble, then that PF is going to be equals to square root of PF times square root of PF transpose, and square root of PF, as we've seen, is made of columns, of m columns, where m is the number of members, each column having the state value for that member minus the ensemble mean. So if you as a consequence, everything here, that correction KH, which starts with that P transpose somehow inside P, KH times the rest is in the space spanned by the ensemble members. Okay? Because the result here, K times Y minus HX, lives in the space spanned by all the columns you have here. So essentially these are the departure with respect to the ensemble mean, but okay. A fortiori they live inside the space spanned by the ensemble members. Okay, and then also here, if you look at the analysis, you also had this value of one member. And so, okay, so all analysis in the end are in the state span in the space spanned by the ensemble members. So, noticing this in EnKF, there is this so-called ensemble transform. And you also, by the way, have the ensemble transform Kalman filter, which relies on the same trick, and you can rewrite actually everything into the space spanned by the ensemble members, or perturbations around the mean of these ensemble members, whatever. So in this filter we tend to focus onto the departure with respect to the mean, okay, in the forecast, and compute the same for the analysis. So working on that space. Okay, you can have a look at observations as well. So I don't think I'm not going to go through too much details, but in the end you have analysis which is equal to some combination of the departure. So departure around the analysis mean are equal to some weightings, if you want, of the perturbations of the forecast around their mean, and the analysis is written also using these perturbations of the forecast around their mean with some given weights. So that you have this formulation, which is used in LETKF. But the other thing I wanted to stress is there is a second key here, which is the L in LETKF, local. The idea is, instead of computing the analysis for all state variables at once, so computing your X, A, M, for every member, whatever, in this algorithm, the point is to compute only the analysis for one component of X at a time. Okay. So it's a big difference, and the thing is, okay, you have a lot of those, because if you compute one analysis, okay, for each component of the state, can be 1 million state components in the state, so it's 1 million, okay, computations. But the good point is that if you have so many computations, you can really distribute them on a large-scale cluster with many cores. Okay, one is going to take care of the computation of the analysis for one state component and for one member, if you have several members. So it's going to be really very easy to distribute. And also the cost for when you make just the analysis for one state component, you're not going to use everything. I mean, you're not going to use all observations that you have in the whole domain. Okay? You will just use the observations that can have an impact onto your analysis. So I put again an example here. If you want to compute the analysis at this grid point, so you have a a model discretized in space like this with a grid, for instance, and here you have a grid point. You want to compute here the analysis for state component that correspond to this one. And so you could have a large domain, but then you will just look at some region where you know that the correlation between the errors on the state variables are high enough, significant, because you know, and so you'll have just then a few observations in that region, and if you're outside that region, you know that's what you have in the PF is going to be low, okay? So the covariances between this point here, the errors at this point here, and the error at some point outside this domain is supposed to be very low, okay? So even if you have observation there, they are not going to have a significant impact on this point. So you can just cut, okay? That's some sort of localization. You focus on observations which are local and can bring something because they are at other locations where you have a correlation with the error on the state. Okay. For an observation to have an impact somewhere at that location where it's not observed, you need really a correlation between errors on the state. Okay, between these two locations, and then you observe one location, correct the other. We've seen that previously. Okay, so that's really the matter is significant covariances between different components in the state, and then you take observations at those locations where you observe high correlation. That's the basis. So it doesn't really have to be like that, a domain like this. It could be something different. I mean, sometimes you can have high correlations. Like you saw with our two waves. Okay, sometimes you have high correlations in other regions and maybe nothing in between, and so it can be more complex than just a square and then taking observations there. You take observations where you have correlation with the state. That's the point. And also here it's just 2D, it could be 3D, and also think that usually you have several variables in your state, like temperature, velocity, pressure, whatever, salinity in oceans, and so forth. So you have different variables. So there is also a question of correlation between the different variables as well. So because you can observe one variable and have a significant correlation error with another variable, and then you would keep the two. So that's a bit more. But that's the idea. And what I think was really important that you'll make this analysis point by point, and then you can distribute a lot. Okay? So that's very relevant for. That's why I wanted to point this one out, and also it's used quite a bit. Here's a reference. So I wanted also to discuss the uncensored Kalman filter because just for give examples, okay? Give you you don't have to understand in all details. It's just for you to feel what's going on. In the Ensemble Calman filter, we sample randomly the error. So we have these members that we make, like we can generate with Monte Carlo simulations or things like that. It's random. In the uncensored Kalman filter, the point is we're going to choose where we also make an ensemble somehow of points, and also compute the error covariance based on that. But then we will choose where to put the points. It's not random anymore. The different states that are made in the ensemble are determined deterministically. Okay, so yeah, so And the error variance, of course, will be empirically approximated with these, and they will be chosen so that the error variance is well approximated thanks to these points. So you, yeah, and the special point, these members will be chosen so that under a nonlinear model, when you will move from one step to the other, your empirical variance will remain of good quality somehow. Okay, it's not only at just when you will start with you will start at some point with XF, just just one state. You have an error variance PF. Okay, and so you replace these by an ensemble of members, which are defined here. And you see you rely on perturbations of the mean in directions that depend on PF, on the error variance, which is logical because that's and then at some distance here you have a coefficient, so you can sample like that and put points. You can have a large spread of the ensemble, smaller spread. And so you can push these perturbations around the mean more or less far in the direction where you actually have errors, which is in PF, which is given by PF. And so and the point is to choose. Then so you choose these points and you put some weights to these points. And when you reconstitute the ensemble mean, then you make a mean over an average over all the members. That's here, that you've chosen this previously, with some weights. It's not just the mean; it's an average, weighted average, which is done so that when we use these weights, we come back onto the XF that we had originally. Also, because we start from XFPF, and then we generate this ensemble of members, and we want that the weighted average of these give us the mean, and the weighted average of the empirical mean based on these members give back also PF. And that's the second part. Here, we put some weights again, so that at the end, we can reconstitute the empirical variance with some weights. So we compute classical, you see the classical error variance, but we have some weights here. And with these weights, we get back PF with the samples we've chosen. Exactly. Okay. So we have some samples, and at least with them, we can reconstitute XF and PF, the original information we had. And also, they are chosen so that in the nonlinear case, then you're going to apply the model to every member, and have then a new ensemble mean and a new error variance. And according to the location where the points were put, the ensemble members were put, we have a good approximation of this ensemble mean and of the error variance. It's actually of second order, while in the extended Kalman filter, it's going just to be of first order. But okay, I think I'm not going to go into much details, but the locations of the points, they catch some non-linearity, while in the extended Kalman filter, you linearize your model, if you remember, to propagate P. Okay? So it's as if it was linear. Here you put some points, and you apply the non-linear model to all these points, and it allows you to catch more about the transformation of the error variance. That's the philosophy with these points. So I'm showing this because I want you to see that you can also because when you make a random generation of members, doesn't really mean you have a very good estimation of your error variance. And actually when random sampling requires a lot of points to converge. If you know a bit about Monte Carlo simulations. Just for the mean, you have, the convergence rate is in the square root of n, 1 over square root of n, so it's very slow in terms of convergence. So and when you put your points at given locations, maybe you can do it better. especially if you know a bit about how nonlinear is your model, what kind of distribution is behind also, behind X. Okay, so in the end, the algorithm looks like this. You have, okay, you start from, XF and PF, then you deduce the XMF at initial time, and from that, you carry out the analysis step with this XMF, okay, using some weighted empirical variances, covariances matrices, and you compute the analysis and its error variance, okay, and from these you generate new members with allocations that we've seen previously. Here it is. In order to forecast, you have your analysis now, you have your PA, so it's error variance, and then you compute you place new members in space, and then you propagate these. Okay, and your forecast is going to be the weighted average of these, and also you have its error variance in the end. Okay, that's the way. So it's just deterministic sampling. That's why I wanted to show that. But there are still issues because you know, here, how many members? Okay, you have nx, the size of the state. Okay, and actually you have 2 times nx plus 1 members, so it's huge. Because, okay, so this is actually you can't use it as such. Okay, but you can then take less points. These points are where you choose to put location of your ensemble members. That's the sigma points, sigma vectors. You can choose other schemes to have less points, but still to have a good approximation. So here you control where you put your ensemble members based on PF. And then you propagate, you make your analysis, then you obtain a new PA, and from that new PA, you reconfigure your ensemble members. So every time you put new members at the location where you think it's better to put them for approximation and propagation of uncertainties. Okay, so it's really under control. It's deterministic. It's not like in the random case for ensemble Kalman filter. Okay, so you have the original paper. So the expert is not here, he was here. That's, if you want more details about these things, I mean, Philippe Moirot has worked a lot around Ensemble Kalman filter, produced a reduced order filter around this. So I strongly recommend you discuss with him if you want more about this. Okay. Another one that I wanted to point out is the reduced rank Kalman filter. So the idea is, all right, we have this, at some point, we also have the mean, we have the error variance, like PA, and we want to, it's too big to propagate, okay? So let's just reduce it. Yeah, in practice, you know, yeah, we said, okay, PA, if the state is of size 1 million, it has 1 million times 1 million components. It's huge, okay, we don't know what to put inside and so forth. But in practice, the main directions where you have uncertainties, and this is the one you want to catch, there may not be so many of them. Doesn't mean the uncertainty is that complex. Well, actually, in practice, it is complex. But at the level where we can get information, maybe we can be happy with just a few directions. Actually, when we make an ensemble of forecasts, in the ensemble Kalman filter, we've seen that somehow our corrections are going to be in the directions of in the space spanned by the members. And these members we just have 30, 100. So somehow the rank of your error variance matrix in the end, the covariance matrix is like 30 or 100 or around these lines. Okay, so anyway, in all these filters that are actually tractable, you have a low rank error variance all the time. So okay, so why not doing it from the start? So we take that PA and we write it in square root form, or approximate square root form, where we take the leading directions into the leading modes in PA, and we put that in the square root SA, and we write the IPA like SA times SA transposed, where SA are just a few columns, or like 10, 30, maybe 100, and that's it. And if we write it like that, then this step, you know, the big problem, how to propagate the error variance, is not so difficult anymore, because here in this one you have you just have to the linearized model here to be called for every column of SA, so just R times, and if R is not too big, like 30 or something, it's perfectly tractable. So you can actually propagate a low-rank error variance. And that's what it is done. And actually, you just have to propagate the square root of it, and the square root of it, of PF, you know, just going to be this one. When you have no error model, because if you have model error, you have an additional term, if you remember, plus Q. Okay. So this is how it goes in these reduced filters. So this is one algorithm, one example, because you have many variants. So you start from XF, again, and then from the square root of its error variance. So you don't have PF, just have a square root of its SF. And you're going to play only with that. So I think I need not write any PF, PA. I just play with SA and SF, so their square roots, approximation of their square root. And so you have KH, you can write it like this. You see that you have always this H times S that appears, or it's transposed, by the way, so it's convenient to compute these things. You can compute the analysis here. And on the analysis, so if you remember, we had this formula that the PA was y minus KH, PF I minus KH transpose plus K or K transposed. It's also equal, sorry, to I minus KH PF. I think you've seen, I wrote it there, A equals the same. So you have I minus KH PF. Usually we use this one because it's simple, I mean, it's the shortest one. But you have a longer expression, which is exactly the equivalent, which is this one, I minus KH PF, I minus KH transpose, plus KR, K transpose. The good point with this one is that you immediately see the square root form. Okay? And actually you can, its square root form is written here. It says S tilde with I minus KH SF, so square root of PF. And so it's in colon, you had this one, this part also, KH square root of R, and you can make the computation, multiply by the transpose, and you will get exactly what we have over there. Okay, so you get PA as you expect. So you need to add columns. That's what it means in this SA tilde. But then this SA tilde is bigger. It's not anymore it's of big size actually. And so if you want to remain of low rank, if you don't have to, you need to project again this SA tilde into a lower dimensional dimensional space, neural space, and you have you can do that for instance, that's what is done here by some projection operator. So maybe you can apply SVD and find the leading eigenvectors and so forth. So, and so that's classically what's done. And then you end up, so you propagate, just you remove the directions that are not so significant, and so that you stay in with or columns in SA. Okay, so at the end of the analysis part, so you compute the analysis as usual, but then you make some operation here to make sure that you remain in low dimension for your square root the error variance on the analysis. Okay. And then you forecast, okay, okay, there is an error here. You start, it's XA, of course, on 72, so you forecast from the analysis. And for the square root of the forecast error variance, it's a bit long, you just propagate the SA, just seen it previously, the previous slide, the end at the bottom of the previous slide. But also you have the model error that comes into the picture. So you had extra columns. So again, you need to filter this to project on a, if you want to keep a few columns in S. Okay. So this operations cost, but then you save so much by just projecting and having just few vectors to propagate here with this. Okay. Okay, so that's just one algorithm, but okay, you can find some different algorithm here. I think the one I've shown is, I think the last one corresponds to the last reference, I think. Okay, there are many other methods, but okay, I think we can stop there onto the working among the Kalman filters and so forth, because it's endless, more or less, so many names also. The ensemble transform Kalman filter, I mentioned it already because it has similarities with EnKF. You have other reduced filters. These are examples, yeah, with two references for these two. People also try to mix ensemble Kalman filter and 4D var. What they want to do is to avoid to have to deal with the adjoint model in the 4D var because it's so complex. And also try to make use of the error variances that are produced in the Kalman that you don't have in the 4D var directly. So that's so they try to use the best of the two worlds. But also it comes at different prices. So okay, I'm not going to get into the details. But, okay, minimax filtering is another kind of filter because we discussed a lot of Kalman filtering, but in the minimax filter you always look for the region where the truth must be. Okay, it's not it's not like you had a distribution, or it's like you had a uniform distribution if you want, and the truth must be inside. So that's somehow a robust estimation. Back and forth nudging. So you have nudging to start with, where you had to your dynamical model a source, and this source is directly proportional to the discrepancy between your model state and your observations. And you have a source so that you get closer to your observations as time goes. And there are some extension of this nudging method, which is used quite a lot, actually, as a very, very simple data assimilation scheme. There are extensions like back and forth nudging, it's called. You can have a look. You will find easily the references. There is a lot of work going on these days on the particle filtering, where the point is to say, okay, we are not going to. We have also some members, ensemble for some members, an ensemble, but this one is not used just to represent the mean and variance. It's also going to represent the full distribution. And then I will play from it using Bayesian rules and so forth. But it's in high dimension because we are we are usually using high dimensional systems. It's difficult to represent the distribution, and so it's still very difficult to apply for large dimensional system. But people are working on it quite a lot. And with this kind of method, you would like to have a lot of members, in order to try to sample the real distribution, not to get the first two moments. And maybe in terms of HPC again, and that could be something to investigate, because you can expect to have a lot of members and maybe do something. Okay, and there are a lot of other methods, and maybe in future methods that you will invent if some of you come to data assimilation community. Okay. So see, there is a lot to do. So we've discussed a lot about ensembles, okay, and I wanted to show other things we can do with ensembles and also how we generate them. I explained a bit. We have uncertainties in the input, the model itself, and so forth. But okay, it doesn't tell everything yet. So okay, there is one part which looks like the Monte Carlo method. You make perturbations in some inputs u to the model. That's what I wrote here. You have some u, which is okay, your reference value, which is given by an expert or whatever, and then you make perturbations around it. Okay, same. And you make your different simulation with these different parameters. That's all. That's one way. And also you can make perturbations on the inputs or initial condition. It can be seen as a parameter anyway. So that's classical. And actually this is very easy quite easy to do it at least to start. And so that's why typically, I mean, the Kalman filter, the ensemble Kalman filter has success because you generate your ensemble fairly easily using this kind of approach and then applying it. And yeah, I would tend to recommend to start with that. If you are your own system want to try like the assimilation, well, yes, try that. Make your ensemble, perturb your inputs, not too difficult, and then compute the analysis, and you're done. Then you have a lot of work there, but you can start with that. And but there are difficulties, of course. Your parameters, your inputs, they may be of high dimension. So we discussed dispersion of radionuclides, for instance, but then if you do that, you have dispersion of pollutants in the atmosphere, but then the input to the model is going to be metallurgical fields, like the wind, and it's not just one direction at Fukushima, it's a 3D field, okay? And you have 3 components in addition for the 3 directions. And you have a lot of other variables in input. So these inputs for big models are going to see to be fields, okay? And sometimes they can even be bigger than the state, because it can be size 1 million or more also. And making perturbation on them is not that simple, because you need to preserve some physical properties. For instance, if you have some fluid velocity, you might want that it remains of divergence free. You also have, if you make perturbations, you have a field, okay? So you don't make perturbations for every point in the field without taking into account the other points in the field, because you have so spatial correlation between the errors in U. So that should be seen in the perturbations as well. So it's not that easy to make perturbation on that kind of field. There are ways to do that, but okay, like I put a reference. But that's okay. That's not necessarily easy to make perturbations. But you can start with simple ones. I mean, you have a field, just multiply the field by one value, and that one value you sample it randomly, and okay, and that's a start. It's better than nothing, but okay, there's still work here. Also, you might want to know which variables are more important in input, on which one to focus in order to have because you can have a lot of inputs, and the question is which one is the most important one to perturb, on which one I really should focus, provide the right distribution, take care of what kind of spatial perturbations, correlation with other variables that I should put. And for that, I just mentioned it, and I put this slide because I like this one. I think it's a good way to have a quick start in the field. You have some methods called sensitivity analysis methods, and with this method, they're supposed to evaluate to which inputs some output of your model is sensitive, okay? And it can even go further. It tell you which part of the variance in your output is due to certain such and such variance of your inputs. So that's partly helpful. But depending on the complexity of your model, whether it's linear or just monotonous, and whether there are interactions between the different inputs or not, And depending of how many model evaluations you can afford, that's here, you can pick one method to try to evaluate to which inputs you are the most sensitive. And this is, you have some methods that are just called screening. So the point is really just to rank the inputs and to say, okay, about which one are the most important, and that's all you know. You don't really trust the exact numbers, but you have an idea of which one are the most important. And the really variance decomposition, here you try to, it's more accurate somehow, you try to know which part of the output variance is due to the variance to such and such input. Okay, and okay, you can investigate this. I just put this one. It was made by Bertrand Yos, who works at EDF, and I think it's a nice overview. You can have a look at the kind of method. I recommend you start also with, for instance, with the Morris method. In the appendix of the slides, you have some explanations. Well, it's just appendix, so it's not so much explanations, but this one is very easy. You make finite differences with respect to inputs, and you'll see. I recommend you start with this one if you don't know where to start. Okay, so that's for inputs, like input parameters. There are also uncertainties in the model itself. We discussed, I mentioned that already. So when you have a model, usually you have different options. If you have a complex model, especially in environment, for instance, you have different parameterization to represent subgrid phenomena. There can be a bunch of physical, biological, chemical processes that are not so well known, and so you have different options to model them. Okay? And this is as many options for making an ensemble of members of different models. I mean, you can construct different models with these different parameterizations or formulations for your phenomena. So what I've been doing, for instance, and you could do, so you just list all the options you have into constructing a model, and then you try to change them, and even possibly randomly. And then it's going to generate different kind of models which relies, you can also change the numerical formulation, numerical solver as well, okay? And maybe you can, and also you would say, okay, I take the best solver, or I take the best physical parameterization, and that's the one I want to have in my model. I think this kind of point of view should not be, I mean, should be forgotten. It's not a good way to do things, because even if you have, you have a parameterization is not so good, actually you'll find that it's going to be better than the supposedly best parameterization in certain situations, in certain locations, or for certain variables. If you analyze your fields, I mean really your fields against observations in different locations and so forth, you'll see that, a model with a parameterization or some description of a given phenomena which is not so great on average over all the domain might be the best in some location or at certain times. Okay? And the same for solvers. You have solvers that are going to perform well when you have a discontinuity, or others that perform better when you have a smooth function and so forth. So you can really mix different, I mean, you can really give a chance to many of them. Of course, on average, the members are not going to be of the same quality, but all members will bring something and be the best somewhere. If you are interested later, I could show some illustration of that, which is pretty striking. You'll see that you have many members and many in ensemble, and many members become the best at some point in some location, although some are very bad on average. So really, don't be, if you're working on the modeling side, or tell the people working on the modeling side to keep options in their model. Not to say, okay, I'm getting a new parameterization, it's the best, I remove the previous one. No, you keep it, and then it's an option for you to make an ensemble. Okay? That's really important, I think, to keep that, because otherwise your ensemble is not going to be so rich. If you just perturb inputs while we have uncertainties in the model itself, No, keep options in your model, and you have easily new ensemble members which are going to be pretty different from each other, and this is interesting information to have. So that's really, for me, it's an important message. Tell that to all people that make models and physical models, and it's true for the numerical part as well. It's an example we made in air quality. So, for instance, in air quality, you have a lot of choices. If you have air quality, you have chemical reactions in the atmosphere between all the pollutants, and there are different chemical mechanisms that exist. Okay, so from one model to the other, you can change. Okay, you don't know this name, but you can change the chemical scheme and mechanism, and you can have many of them. You can change the way the vertical diffusion, the way the vertical turbulence is modeled. You can also have different ways to compute deposition velocities of pollutants on the ground and so forth. You can have, you can use different databases for the vegetation, for instance, so the land use cover, for instance, because deposition are going to depend on that, for instance. You can have different ways to compute the rates of photolysis reactions. And on the numerical side as well, you can have different options, even just the discretization. And with just this, these options here, I think, okay, you have already 2 times 10 to the power 5 simulation, different members that can be built. And actually, we have a longer list, and pretty soon we end up with, we can make, I think it was 200, what was that, 200 billion models or something, because it's combinatorial, so it can be very big soon. So you need to keep those options, and what we did is that we randomly picked the options and generated new members this way. So, and why not? And when you do, so we did that for 100 members, and the funny part is within these 100 members. There was at least one member which was better than the model that was tailor-made by the modelers. That had better performance over a long period of time. So by picking just randomly over 100 members, you can find already a model that is better than the one that is really fine-tuned by the modelers, trying to find the best parameterization and so forth. Okay, so that gives some perspective, I guess. And so this is, for instance, ozone maps for 2 different models. You see that you have really different kind of patterns. Some patterns will keep the same because all the models have the physics behind. It's not just random models. Okay, you still have ozone peak in the day, lower ozone in the night. You have the same kind of shape for many things, but also big differences in certain for certain things. So, yeah, I encourage you to also to consider having these multimodel ensembles, not only perturbation in the inputs. And I think since we are talking, we have this HPC. Ideas here. I think something that has not been explored too much is what we can do with very large ensembles. Okay, because usually we play with 20 or up to 100 members in our ensembles, and we don't try to get too much further because it costs a lot. But if you have a lot of computational power, how interesting is this? So we are involved. My team in a project. For meteorology, to try to have 1,000 or more members of weather forecast and see whether it's helpful or not. And I think this is a good direction. So, I think that's research. There is research here to be done. How to build so large members so that you don't have so that the new members are not correlated so much to the previous ones. I mean, you really want to explore and not to have too many redundancy in your ensemble. So there is research to be done here, and I'm pretty sure that with large ensembles we could do something that different from what we're doing now. Because at the moment we are really exploring very low dimensional error spaces, Not saying it's wrong, maybe, okay, our main errors maybe are in a small dimension, possibly, but I don't know, that's a question for many fields. Also, with adequate methods from a big ensemble, you can probably extract a sub-ensemble, which is good for uncertainty quantification, or which is good for to improve the forecast. That's also a research direction, I think. Because, okay, it's very difficult actually to describe the uncertainties. You saw with this just shallow water model, if we had to prescribe the B, it was really tough already, and very simple for a simple model. But if you have very complex model with lots of inputs, phenomena, parts are just black box, you don't even know what's inside, and it's very difficult to know what to do. And so I'd recommend that you shake everything. You make different kind of models. You make perturbations, possibly very high perturbations. You don't care. You modify a lot of things, and then you really explore those large ensembles, okay? Because you don't know where to go exactly, so you go in many directions. And after the facts, then you try to post-process and filter out your members, and I think that could be pretty efficient. So we did that for. I don't know if okay, no, not have the example here, but we did that for uncertainty quantification, for instance, and we had not a very large ensemble, it was just 100 members, but after filtering, we got only like 30 members, which we could show had a very good uncertainty quantification, because we removed the members for that, and then we showed that it worked well, including in forecasts and so forth. So I think that's something to be considered. Okay. Okay. So ensembles are used in Ensemble kind of filter, as are used for uncertainty quantification, obviously, and can be used as well to construct some meta model. Maybe I'll have a look. We'll have a look at that, and for aggregation in order to improve the forecast, because when you have a lot of members, so you can make data assimilation and so forth, and then. And your forecast is going to mean the ensemble mean of all the members. Okay, the EnKF is going to be the average of all the members in the forecast, and hopefully you'll improve your forecast also. Okay, that's one way to go. Another way to go that myself I've been exploring quite a bit is you do nothing. You just let the models run, no assimilation on them, but after the fact you combine them. And so you try to put some weights on these members after the fact, and then have good forecasts. Okay, so I think I will go very quickly here. When you have an ensemble of members, you can have some. There are some scores to evaluate how good it is. When you want to know whether one simulation is good, what you do, you make a comparison with observations. Okay, you compute just I don't know the root mean square error between observation and simulations, and you're done. It's easy. You make correlation, a bias, whatever. But when you have an ensemble of members, somehow you have samples on a distribution, and on the other hand, you have one observation, for instance, at a time. And how do you compare these? They are not of the same nature. Because we have a probabilistic somehow forecast, and you have just one observation. So it's not that so easy to compare the two. And yet you would like to evaluate how good our ensemble is. And the only additional information we have for that is the observations. So we need to make sure to make use of observations in order to evaluate ensembles. And that's the point here I wanted to make. I think I'll go fast on that, but. For instance, you give you some idea. We want to that the ensemble members and the observations cannot be distinguished. So if I give you a time series of ensemble members and a time series of observations, and if you can pick the one which is the observation, it's not a good sign, basically. And if you can't really make the difference between the ensemble members and the observation, then you have the so-called consistency property. So if you, for instance, you have your ensemble simulation like that, and your observations Okay, you don't. Of course, you don't want to have your observation here, a bias. You don't want to have this kind of behavior because it's not the same behavior. But if you have like that, the same kind of behavior, then okay, it's a good sign you're fine. And one way to check that is to compute the so-called rank histogram. I think it's you have your ensemble members, and every time you have an observation, I'll put one observation here. You compute its rank. So and the rank is the number of members that have a lower value than the observation. So I put it here, and I have 1, 2, 3, 4 members below that observations. So the rank of this observation is 4, and if I have a new observation here, its rank is 0 because I have no members just below. And if it's on the top, then it's 5. And so forth. And for all observations, from different locations, different times, for the same variables usually, I compute the rank of many observations. And in the end, we can show that we expect, if we have a proper sampling of our errors, we should have the same number of observations for every rank. So here we have just a 5-member ensemble, very small. But then we plot for the different rank. So we have 0, 1, 2, 3, 4, 5. We print the number of observations with that rank. Okay. Hopefully it's going to be about flat, like that, for instance. Well, okay, I did not center. But okay. You should have something like that. And if you end up, for instance, with something like that, which is usually what you have if you start your first ensemble and compare, it means that you have a lot of observations below the lower envelope of your ensembles and a lot of observations above the upper envelope of the ensemble. You have a lot of observations here and here. So it means that your ensemble is under-dispersed. It's not enough, you don't have enough spread in your ensemble. You've underestimated your uncertainties. That's usually what you get in the first place, because we tend to underestimate the uncertainties. And you have the reverse, which would be this one. Then you have a lot of observation in the middle of the ensemble. So if you have this kind of reversed U-shaped, it means that you overestimated your uncertainties. So pretty rare. That can happen. Okay, and another shape you can see, it's not so easy, maybe this kind of shape. Okay. If you have this kind of shape, it's probably because you have a bias. So you have a lot of observations that tend to be here, so you have a negative bias most probably. And so it's good to, you can compute the variance of this histogram, and hopefully it's going to be 0 when you have, and so it gives you a score. I mean, it gives you an objective score that you can minimize in order to find the best ensemble somehow.
You do that for each component of the observation?
Well, you do that. Usually you need a lot of observations.
So if the observation is vectorial, you compare for each component independently?
Well, it depends. Well, if you'll use all observations of the same variable. Like if you have temperature at different observation stations, and your observation vector is just all this temperature, then you'll use all of them to add to the ranks. But you might decide, okay, I'll just take for France. Then okay, and yeah, that's.
So you are somehow doing ensemble of type of observation.
Yeah, you can make for different kind of observations. When it's multidimensional, actually, I think, yeah, you also can, because you can also do multidimensional using other things like minimum spanning trees. You can have a look at this. It's another way to compute a rank when your observation is a vector. But if it's the same variable at different locations, probably you can just use them as just scalar observations in order to have a lot of observations as well, because you need also quite a lot for these to converge. Yeah, but building on the consistency, you can even build your own actually rank. The rank is computed yeah, so that you can exhibit this consistency property, that the observations are not different from any member. So you compute the, okay. This is an example of a calibration. So this is that's for 100 members in air quality of a rank histogram, which is not so great. And after removing like 70 members, you get this one. If you remove the proper ones. You know, and in forecast it remains good. You keep having a good rank histogram. So that's what I mentioned previously. Like you generate a bigger ensemble, just select a sub-ensemble which is representative of uncertainties, for instance, according to the rank histogram, and then move from that. Use it in forecast, and it gives you pretty different uncertainty quantification. You know, after calibration. Yes, that's the standard deviation. So of your field. So the diagonal of your PPF, if you like, square root of the diagonal, and you see some differences. There are other properties like reliability. That's more for probabilistic forecast. And okay, we move into probabilistic forecasting, sharpness, resolution. Okay, I'm not going to, but yeah. Have a look at this if you want to evaluate an ensemble. Here you have all the links. One is especially interesting is also this CRPS, which is a score. You compute the you have an empirical cumulative distribution function. So, for instance, that's more empirical cumulative distribution function. So it starts 0 and ends up at 1. And from the ensemble, you can build 1. So if your ensemble, you have x1, which is here, x2, which is here. Okay, I assume it's sorted. x3, which is here. You will start from your empirical cumulative distribution function will be 0, and then it's going to jump here as well, and jump here as well, and here you will reach 1. So that that's a probability. This cumulative distribution function f is the probability that the value is lower than x. Okay, so I plot this f against x, and for the in the ensemble case, you can build this cumulative distribution function like that. And when you have an observation y at some point, we assume that the cumulative distribution function is this one, just a step function at the observation. And then the CRPS, it's you just compute the two norm of the difference between these two distribution function, cumulative distribution functions. Okay, and if you want to have a better one here, probably you'd like to, because you can then put weights on the members, which would represent the step you have here in your function, and to be closer to observation, then you would put 0 here. So you would have something like that. Here you would put some value, maybe to arrive about, I don't know, the middle somewhere, and you would have something like that. And this one, the square difference will be minimized compared to the previous one we had. So we can try to find weights onto the associated to the members in order to have a better CRPS. Okay, it's going a bit far, but I think it's a pretty interesting topic. Okay, you have some references about these things. I especially like the first book, although it goes much further than ensembles. Good one. The website is good as well. Okay. Okay, I'm not going to go into the Bayesian stuff. It's nice, but it's not really necessary. It's also a way to see that we need to make some. We can make use of some reduced models or meta models, which are models that run very, very fast, potentially, but give similar results to the original model, which costs so much. Okay? Because you've seen that we already have these computational issues, especially in the propagation of the error variance and the number of points we can afford, because the model costs a lot, and or it's linear version and so forth. This costs so much. So there are approaches where we try to replace that big model that costs so much by another one that is very fast, not exactly the original model, but still has gives similar results, and hopefully, since it has similar results, we can estimate uncertainty with that. I think, okay, I'm going to skip it for the moment, just telling you what it does. So we make a dimension reduction first on outputs, possibly inputs. And after this dimension reduction, we end up with a reduced model which has few inputs and few outputs. And then you can make a lot of calls to this reduced model and try to infer what is the relations between inputs and outputs. And this is a part where actually HPC would be very interesting, because it can make a lot of calls in order just to build that meta model by training it with a lot of calls to the model. You train it, and so I'll come back if we have time. I think not. So I just mentioned it because this is I think many people are heading toward this. And yeah, can show you already good, interesting example if you like after this presentation. So I wanted to also give you show you a method for ensemble forecasting with so-called ensemble forecasting. So the point is to put weights to the member of the ensemble in order to make a better forecast, not just computing the ensemble mean, but doing something better in order to be closer to the observations. So observations or, okay, analysis or something you get after the facts, which is what you would like to forecast before the facts, before observations are available. So we have this forecast here, XFH, you recognize this thing, and it is just a linear combination of the forecast of the members. And here you make no data assimilation. The members are just well, you can, but it's not necessary. Okay, it's not the point. So I'm not going to show you any XA here. No XA, just your forecast XF, and the ensemble of forecast XFM for all M's. And the job is to find the weights you at every time H to apply to the different models in order to find to produce the best forecast XFH. Okay, and we have some verification or observation, or it could be an analysis out of data assimilation after the facts using the observations, which is YH here, and we want XFH to be as close as possible to YH. So we'll try to find the best weight for that. And so here is the game. So at time H-1, we have the forecast for the current time H-1. Also, since these are forecasts, we know them for the next step. So we have XMF at time H as well. From that, we are going to compute some weights. That's our job for the next step, UM. Okay, and with that, we combine the two and obtain XFH, which is our forecast, our so-called ensemble forecast, which is a linear combination of all the members we have in the ensemble. But at time H-1, we still don't have the observation YH, but it's going to be revealed the next step. So at time H, we obtain YH, okay, and we obtain also the forecast for the next step in the ensemble. So we update the weights based on what we've seen previously when we compare YH and XFH, so our performance, and we produce with these new weights, we produce a new forecast, a combination. And to do that, you can do that, for instance, in this way. Oops. the weights UH, it's going to be the vector of weights, which minimize this form, which is in this case quadratic, where you have here some, okay, here you have for the past until times h minus 1, because at time h you still don't have observations, of course, but until time h minus 1, you compute this difference between the aggregated forecast with the weights, average forecast here, weighted average forecast here, and the observations for all the steps before. And somehow you select, if you forget this or W, you select the weight vector, which would have given the best performance over the past. Okay? So you look at some W that does not depend on time. You just take the best weights for the linear combination to be as close as possible to all the observations from the past in the square root, in the square sense, if you will. Okay. And also you have to add actually a penalization here of second order or others of the two norm on the two norm of this vector W. It helps smoothing out, if you want, the forecasts, and you take the vector weights that would have been the best over the past, all the past. Okay, you take it for the next step. And after that, and for the next step again, you have the observation will be revealed, and then you will be able to update again the test weight vector, and you do that again and again, so that you obtain a new sequence of forecasts. So that's a sort of assimilation in the sense you don't correct the state directly, but you compute a new state by linear combination of all the states using the observations. So it's, I think, at least a merging between observations and simulations. Okay, there is a, you can have some discount terms so that the faraway path does not count so much in this quadratic form. Okay, it's getting late for this kind of details. And the good point is, with this kind of approach, you can show without any stochastic assumptions. That's the difference with what we've done so far. Without any assumption, essentially, except that actually the ensemble members and the observations are bounded. You can show that the performance of, so that's the quadratic performance here, of our forecast with this UH, these weights that depend on time that we forecast for every time, every step. When we compare it to the best, to the quadratic discrepancy between the aggregated, between the observation and the weighted ensemble mean with weights that do not depend on time, but the best. So you take from the past the best combination, okay, after the facts, and you compare it to the combination we've made ourselves. But we updated the weights online, okay, without knowing the next observation. So that's so we had the chance to update the weights every time. While here we take only the constant weights, but also we were trying to forecast the observations that we don't know. Okay, that's more difficult in that respect. And so, and the quadratic error of our forecast minus the quadratic error of the best linear combination over the time period actually goes down to below something that is almost zero on average. Okay, so if you, in other words, it means that your performance in terms of forecasting when you make this combination in the long run, because it's it's asymptotic bound. In the long run, you will be at least as efficient as the best linear combination of members, which means that you will be at least as efficient as any member in your ensemble, because it's just a weight where you put 1 for this member, 0 for the others. You will be you have better performance at the ensemble mean, which is usually the one which is chosen, and this is true for without any assumption essentially. So that's efficient. That's been used in different different fields now. yeah, including it's tested by Meteo France now for their forecasts. So and this one, okay. The point also here, you imagine that you can make a lot of simulations. We have large ensembles again thinking about HPC and some directions that might be relevant for it. You can have a lot of simulations and then putting weights after the fact to them. If you have too many members, determining the weights might be a problem for some algorithms, but there are algorithms like the Lasso one, which are called sparse algorithms, sparse learning methods that are especially made for that. So they will put a lot of zeros to many members and just focus on a few of them. So there are methods to do that. I mean, the machine learning community, and that could be used in combination with a large ensemble generated with some HPC. So that's something I think to investigate as well. And this is a result. So this algorithm that you've seen is applied on every grid cell independently of the others. Because you see it's here, everything is scalar in the linear combination. Okay, here it's just scalar, but you can do that for every grid point, every state component if you want, independently of the others. Or at every point where you have observations or analysis, because you can use analysis instead of observations if you like. When you, oops, okay, I'm lost. And so this is a reference, that's an average over 1 year. And this is what we want to forecast, actually, it's analysis. So that's after the fact that the best estimate we have on the ozone field. I mean, it's an average over 1 year, and this one is the forecast without anything, just the forecast for one model. This is a forecast with data assimilation, like I think optimal interpolation. And you think it's a bit better, but still very far from it, this one. That's because it's an air quality model that runs, and air quality models, they tend to forget quickly what they've learned. So you make correction on them, and they're very stable, and then forget after some time what the corrections you've made. So data assimilation, like this, like optimal interpolation, is not that efficient, not useless, but not highly efficient. And this is aggregation. You see, on average, it's very, very close to the analysis what you want to have. It's not true for every step, of course, but on average, at least, it's pretty good. Okay, these are the weights. You see that move. So you can put some. Actually, you can also do the same and apply Kalman filters on the weights and so forth. So on minimax filter, we've done these kind of things. And here you have all the members. In red, that's what we want to forecast. And in white, that's all the members. And we put weights to them. And in the end, we have some tube where the uncertainty should, the truth should be. And the estimate is the white one. So, you know, you can really make, okay, you know, things straight after some, as an example. So there are some references that I put as well. So I wanted to finish with two things. First, some advertisement. We have a data assimilation library you might be interested in, where we have many algorithms that are implemented. It's open source. It's LGPL, so it's even easily usable for business if you want or what. It's written in C++. It has a Python interface, so you can write your model in C++ or Python. It's available on INRIA Forge here. Yeah, so what you expected to do is when you want to use that, you come with your model in whatever form, and then you write an interface on top of it in Python or C++, and you have a given contract. So you need to provide like a get state so that you give the state to Verdandi, or get parameter variance, for instance, because if we want to make perturbation on inputs in Monte Carlo or whatever. So you have a number of methods of functions like these ones. Not the same for every method, but they are consistent across the method. So when you implement it for one method, it's going to be used for another if it needs it. So you write all the interface, and then you can use the algorithm. So the algorithm is already implemented. There is parallelization, even distribution of big state vectors on different computers, because you might have also limitation in memory on one computer. It's not only always just for a matter of computational power, sometimes problem of memory as well. So you have a lot of things that you can find, and you might be interested in them. It's applied to real applications, and And so it was developed at INRIA together with Philippe Moirot and Dominique Chapelle, and Gauthier Bureau contributed to it. Who is here today, so you have experts around also, and you will be welcome to discuss about this library if you are interested. Okay. And I wanted to finish, to conclude, to a bit motivate you about applications. And so data assimilation is really important in methodology. I mean, it has improved quite a bit the forecasts, and probably more than just improving on the models themselves, because bringing observation really made a big difference. So but these are classical applications. Like in geosciences, it's been used a lot. And now it's moving in other fields, and also new changes somehow, not so classical fields, like in biology or medicine. So Philippe is working a lot on these topics with his INRIA team, so that's a new field for data assimilation, and that's very exciting. We're working also on urban pollutions, for instance. So now you've heard about smart cities, and the fact we have a lot of new sensors, possibly mobile sensors on the smartphone, and big data that's coming because we have more and more sensors everywhere. You're going to hear about it again and again for the next decade at least. So we have a lot of sensors, and also we have simulations now. It's something that is established now. Simulations of traffic, of air quality, of noise pollution, and so forth. So we have all the components, and we need to put all of them together. And there is a lot of work in academics, in the industry, and so forth. So hope you. And I'm going to illustrate a bit with that. So that's an example of things that are going on. We have a mobile application which is called Sound City. It's going to be renamed in Ambicity because it's going to be go further than the sound issue or the noise issue. But it was released with the city of Paris during a press conference. So that's something, people are interested in these kind of things. And so we have an application on the Google Play and App Store, and it measures, with a microphone, it measures the noise levels, either automatically or during the day, or intensively around a journey, like you can see here. And the point is, what to do with this observation and the noise simulations that exist as well, and to merge the two with this kind of maybe low accuracy measurements, but that come in pretty big amounts, and which are mobile and so forth. So we have simulation of air quality in the forthcoming application as well, and so we want to merge all this kind of information in order to improve the maps. And here, for instance, that's kind of, for 1 hour, we can get, these observations from people contributed in Paris, noise observations, at some location. And then for 8 hours, we have this. And so you imagine you accumulate all these. So at the moment, we have 55 million observations in our database, and it's growing. So, and then you have all this data that you have to exploit in order to make the best estimate of the noise pollution, of individual exposure to pollutions, noise, and also air quality. And you have correlations between the two and so forth. So there is a lot to be done, So hopefully we'll be able to count on you and on people also advertise. Let's see an example of data assimilation. That's an air quality map. Here you have point observations, which are from a fixed monitoring this time. It's not on smartphones, but it's going to happen sometime. And then we make correction after data assimilation. So this is XF, okay? And this is XA, okay? So after correction. So you can have pretty big corrections. And these are other examples. On the left, you have nitrogen dioxide concentrations as simulated by a model. And on the left, it's after data assimilation, an assimilation of the observations. So we do that again and again. Sometimes the model is okay. You don't have too many corrections to do. But sometimes you have more corrections. So, and this is now installed and operational in several cities. So that's concrete things also. We have seen a lot of equation algorithms, but in the end also it's very concrete. Okay, so, and I think there is a tool. I mean, you have to work from the methods themselves and improve them even on the theory, and then go to the software and down to the application, and then let people use it. So that's a challenge also. And I think, and this one is for noise. So here you have noise simulated by a model, and this one is after assimilation of mobile observations in the area where we see that's not as big as anticipated, which is good news. Yeah, that's kind of nice application where we need also potentially a lot of computational power if you want to do that for many cities, many observations coming from many kind of sensors. So that's not, that's just new beginning. Okay, I'm done.
Thank you very much. Any last question before we close the summer school?
For the last method you have presented, the one I think is on slide 91. Yeah. Does this work across multiple models?
Yes. The thing is you need to have every model needs to be like a forecast to be aggregated, so a forecast at the same location, but you might have to interpolate if you are not on the resolution. But you can take any model. There is absolutely, even if the ensemble is not representative of a set that is whatever, there is no assumption whatsoever on the ensembles. It comes from whatever you want. Yeah.
Okay, thank you.
Other questions?
Just one. How long are the computations of what you've shown?
Usually, if you make just an analysis, it's going to be maybe it could be 15 minutes, 1 hour per license. It's not that huge, but then you will maybe want to do that for 1 year, okay. And one analysis would be for 1 hour. You know, so it can be very big if you want to make long time series, for instance. It can be difficult if you want to real time, because if it takes 1 hour and you want to forecast, provide forecast every hour, then you need to parallelize and then you can speed up. Yeah, and for the ensembles, that just it depends. It depends on the model. The thing is, it can take a few minutes, for instance, to compute, say, 1 day of simulation, or 15 minutes. But then when you have 100 members, it takes quite a long time already. You're almost at the same time as the physical time, and if you want to do that for 1 year, that's going to take 1 year of simulations. So that's why we are moving also toward, so we parallelize, but if we want to go even further in terms of instance quantification, that we really need to go to the meta modeling at some point. Because then we can have some applications where it would take like 4 years to compute the ensemble we would like to have for over 1 year. Yeah.
But maybe the question also about the data simulation part is quite cheap with respect to the forecasting part. So for people from modeling, actually using the data should be understood that's something which is quite cheap with respect to the modeling part.
Agreed.
Do you make a choice with all the data you have? Because you don't take every data? So
well, in practice, we could. The thing is, in the matrix R, the R variance, we put the confidence we have in observation. So we can, in principle, we can put all of them, and then put a very high error variance on some of them, just for them, so that they do not have so much influence. But then it costs more in the computation, so we remove them if they are not going to bring anything anyway in practice. So in theory, we should take all of them. In practice, we'll take just those that we think are going to bring something significant.
It's true that at one time, when data will be so big, it will be then cheaper to have the model, but we are not at that moment yet.
Yeah, and then you have these tricks like localization that I've shown you. Just focus on the region where you can have some significant influence because of the covariance errors, and then you just take observation in that region. So you have tricks, and then, but it can cost quite a bit when you're moving to assimilation of images. People working on satellite images and making an assimilation for that, and there you also have new applications like in agriculture, for instance, that are very very interesting perspective with satellites with very fine resolutions that are being launched by, that's another topic I should have listed, by the way.
I have maybe last question. For the last model for the last application, do you plan to also integrate some traffic modeling in order to have a modeling of the sound inputs from the biggest sound inputs?
We're working on the traffic part as well. So there is a project. I have a PhD student working on traffic modeling and uncertainty quantification for the traffic. So and then we want to propagate uncertainties in the traffic model, in the computation of the emissions from the traffic, because our uncertainty is also in the computation of the emissions, and not only because of Volkswagen. And then we propagate those into the air quality model as well. So we want to have the full chain and later on the noise as well. Yeah, there is also something, because we want also, you need, when you do the data simulation, somehow you also must be ready to work with different kind of models. I think that's very interesting, and we want to have these chains with physical model of different kinds, and you work with biological models, and I think that's really interesting as well to judge these models and have some and have methods that you can apply to different fields and make them talk together in the end, because you have a big chain of computations. So that's also interesting, I think.
Other questions? Okay, so thank you very much, Vivien.
Thank you.